Take a look around you. Everything you can see and touch, the device you're watching this on, the chair you're sitting in, even the air you're breathing, it's all held together by this invisible force. It's like the glue that builds our entire reality, right from the atomic level. So today, we're going to break down that force, chemical bonding. You know, it's a pretty wild question when you really stop and think about it. Why aren't we all just floating around in a giant soup of individual atoms? Besides a few loner elements like the noble gases, atoms almost never fly solo. They're always linking up, forming these incredibly complex structures that make up our world. So, what gives? What's the big motivation? Well, the answer is what we call the chemical bond. You can think of it as the universe's own brand of superglue. It's this fundamental attractive force that pulls atoms together, building, well, everything. But where does this crazy strong attraction even come from? It really all boils down to one simple, universal idea: stability. Just like a ball will always roll to the bottom of a hill to a place of rest, atoms form bonds to get to a lower, more stable energy state. See, bonding isn't some random hookup. It's nature's way of finding a little bit of peace and quiet. Okay, so how do atoms actually find this stable state? Well, back in 1916, a couple of chemists, Kosel and Lewis, found this huge clue by looking at the celebrities of the periodic table, the noble gases. These are the elements that are famously stable. They're too cool to bond with anything. And their secret? Well, it gave us our first huge rule in chemistry. And that secret is all about this number, 8. It turns out that noble gases have this perfect full outer shell of 8 electrons. And that configuration, it's exceptionally stable. This octet, as they called it, became the magic number, the state of electronic perfection that pretty much all the other atoms are trying to achieve. And that observation, well, that leads us straight to the octet rule. It basically says that atoms will give, take, or share their outermost electrons, we call these their valence electrons, all in an effort to end up with that full set of 8. These valence electrons are the only ones that really matter for bonding, because they're right there on the front lines, ready to interact with other atoms. So if the ultimate goal is getting to 8, atoms have two main strategies they can use. They can either just transfer electrons from one to another, like a straight-up giveaway or, a theft, or they can come to a more diplomatic agreement and share. So let's see how these two different playbooks create the two main types of chemical bonds. This slide lays it out perfectly. On one side, you've got ionic bonds. A classic example is table salt. A sodium atom just gives away its one lonely valence electron to a chlorine atom. So now, sodium is positive, chlorine is negative, and bam, they stick together. Opposites attract, right? Pure electrostatic force. On the other side, you've got covalent bonds, like in water. Here, the atoms don't transfer anything. They cooperate. They share electrons to complete their octets, forming these nice, distinct neutral molecules. Now, to keep track of all this electron sharing in covalent bonds, chemists came up with this really handy tool called a Lewis dot structure. You could think of it as an accounting system for valence electrons. It lets us draw a simple 2D map of how a molecule is all connected just by following these few straightforward steps. So let's try it with our water molecule. If we map it out using a Lewis structure, it looks super simple, right? You've got an oxygen atom in the middle, sharing electrons with 2 hydrogens on outer side. On paper, our blueprint shows a perfectly straight line. H-O-H. And right here, our simple model hits a wall, a really big one. The Lewis structure is great for counting electrons, but does this flat 2D drawing actually represent reality? Is a water molecule really a straight line out there in 3D space? And this brings us to something really profound. A molecule's actual 3D shape is every bit as important as the bonds holding it together. The octet rule gets us the right connections, sure, but it tells us absolutely nothing about the geometry. To go from a flat blueprint to a real building, we're going to need another layer of understanding. So, back to the question, is water a straight line? The valence shell electron pair repulsion theory, and we'll just call it VSEPR, because that's a mouthful, gives us a loud and clear answer. Absolutely not. And the reason why has everything to do with the electrons themselves. The core idea behind VSEPR is actually beautiful in its simplicity. It just says that all the pairs of electrons in an atom's outer shell, whether they're in a bond or just hanging out, are negatively charged. And what do like charges do? They repel each other. So to keep their distance, they push each other as far apart as possible. And that simple little push is what dictates the molecule's final 3D shape. But, and this is the key detail, not all this pushing and shoving is equal. VSEPR tells us there's a clear pecking order. Lone pairs, those electrons that are not tied up in a bond, they take up more space and they push with a lot more force than the electrons in a nice tidy bond. So the strongest repulsion is between two lone pairs, and the weakest is between two tidy bonding pairs. And this is where VSEPR theory just absolutely shines. If a central atom has two groups of electrons, like the carbon in carbon dioxide, they push each other to opposite ends, creating a perfectly straight, linear molecule. But now let's go back to water. Oxygen has 4 pairs of electrons around it. 2 are bonded to hydrogen atoms, but the other 2 are those powerful lone pairs. And these 2 lone pairs exert a huge repulsive force, pushing the 2 hydrogen bonds down and closer together, forcing the molecule into its famous bent shape. The mystery is solved. So we have the type of bond, and now we have the 3D shape. Let's put it all together. Because when you combine these 2 fundamental ideas, you suddenly have the key to understanding the properties of, well, literally everything. Okay, so here's the big takeaway. The bond type sets the stage. Ionic bonds make hard, rigid crystals, like salt. Covalent bonds make individual molecules. But it's the molecular shape that directs the whole show. That specific bent shape of water, that is precisely what allows it to form special connections that make it a liquid and the solvent for life itself. That perfect tetrahedral arrangement of carbon atoms, that's what gives a diamond its legendary strength. Bond type plus shape equals function. It's that simple. When you look at it that way, it's really incredible, isn't it? These simple rules of attraction and repulsion, of sharing electrons and just trying to get stable, they're nothing less than the architectural blueprints that construct our entire material world. Which, of course, leaves us with a really powerful, forward-looking question. From designing new drugs that can fit perfectly into a virus, to engineering brand new materials with unbelievable properties, the potential is just boundless. If a molecule's shape dictates its job in the universe, what can we create now that we understand the rules of the game?